So as it contracts, it gives off heat, but it gives off radiation, but at the same time, it heats up. It doesn't cool down because of this radiation. So it's just that this falling of the gas inside, it has potential energy. Half of it is going out as radiation, and half of it is being used to heat it up even further. And what happens is that when it heats up further, it gives off more radiation, because that's what the Wien's law tells us, or Stefan Boltzmann law, that if you're at high temperature, the thermal radiation has to go out. You heat up anything, it has to radiate. So the gas radiates. When it radiates, it gives off energy. Where does this come from? It has to come from the contraction. It comes from the contraction. But the contraction ends up heating it further. So it's a runaway process. The gas contracts, heats up, and as it heats up, it gives off more radiation. But that radiation doesn't cool it off. It makes it contract even further and makes it heat up even further. That can only stop if we have another source of energy which can provide for the loss which is going out in the form of radiation. So that you don't have to provide the gravitational energy. So gravitational energy is no longer going to be the source of this radiation which is going out. And in a sense, this source will be set at a rate so that it gives off exactly it keeps a constant temperature. And whatever heat is lost because of this temperature is then provided by this internal source. So it's just like you have a bulb. You heat it up and it's giving off light and heat. It doesn't cool down because you're constantly providing it an electric energy, electric current at a constant rate, which replenishes whatever light is going out. So you have to give this kind of a constant source. And this comes from this nuclear furnace inside the stars. So nuclear furnace is based on basic nuclear physics, or you can call nuclear chemistry. Nuclear chemistry is a more appropriate name because one should think of nuclear reactions just like the chemical reactions. In chemical reactions, it's the atoms which rearrange themselves in different chemicals. And those rearrangements sometimes release energy and sometimes they require energy, right? If you have a molecule of some hydrocarbon, like methane gas or a petroleum molecule, you bake it off, it releases energy. But then there are other molecules, like water. It's very stable. If you want to bake it off, it won't release energy. You will have to give it energy. So the same kind of things happen inside the nucleus. Nucleus is composed of neutrons and protons, and they are like arranged inside the nucleus. So some nuclei, if you bake them, so you have think of a nucleus as a molecule of neutrons and protons. So some of them, if you bake them, you release energy, and for some to bake, you have to provide energy. The difference between atomic chemistry and nuclear chemistry is that the atomic chemistry is based on electric forces. There's force between charges, that different electrons and nuclear electrons which have charges on them, which bind different atoms together inside the molecules. And it's this force, think of them as springs, electromagnetic springs. So when they get rearranged, you get some energy is released or you have to provide it. In case of nucleus, what is binding them together is not electric force, because electric force cannot bind them. They are composed of protons and neutrons. There are no opposite charges. So there's no attraction. There's only repulsion. The natural tendency is for this thing to break out. There's another extra force called strong nuclear force, which binds them together. And it's a much, much stronger force, 100 times stronger between two protons compared to the electric repulsion. But it's a very short range force. That's another difference. So two differences. One is it's very strong. So what does very strong means? It means that the energy is involved. So like if it's a very strong bond and you want to break it, you have to give it a lot more energy. Or if it's a very strong bond and there's some energy involved so that you break and some energy comes out, usually it's a lot of energy which comes out. You had a question.
Yeah, what is the name of this force?
It's just a very natural name, strong nuclear force, not a very inventive name. Strong because it's strong, nuclear because it's inside the nucleus. Well, if you know, at the fundamental level, there are only four forces in nature. Every phenomena which you ever see in the world is based on these four forces. One is gravity. We all know that. We are familiar. We have studied a lot about it in this course. One is electromagnetism, which at least we use a lot of components in our life. So we know that this force exists. Actually, all the chemistry and all other solid state, like you want to make a material and you say that this is a strong material, this material has this property, that property. We have invented a new material. We have made these chemicals, these new medicines. All of that is essentially electromagnetism. It's just rearrangement of atoms based on the electric forces between electrons. So everything we see in ordinary life is either gravity or electromagnetism. But actually, there are two more forces which are not very obvious in our everyday life. And one of them is strong nuclear force, which keeps the nucleus together. And one is called the weak nuclear force, which kind of breaks apart the nucleus for certain reason. We will come to that as well. So apart from these four, there's nothing else. So nuclear force, as I said, that is a strong force, but it's a very short range force. It only acts when you bring these protons and neutrons close together to a distance of 10 to the minus 14 meters. So that's like 10,000th of the size of the smallest atom. So nucleus, that's why nuclei are very, very small. They are much smaller even compared to the atom. And the funny thing is that they don't feel, protons and neutrons do not feel this nuclear force. So first of all, this is only between proton and neutrons. Electrons don't feel it. Only protons and neutrons feel it. That's why they are the only ones who are inside the nucleus. Electrons is not bound there. But also they only feel it when they come very, very close. Like gravity, if you're far away, if I'm far away from Earth, the force is weak, gravitational force becomes weak, but I can still feel it. I'll still feel it. An apple falls near the Earth at 9.8 meters per second, but the moon is falling towards Earth as well, but it's falling at a much smaller rate because the gravity is weaker because the moon is farther away. Not so in case of strong force, nuclear force. It just stops. As soon as you increase the distance from 10 to the minus 14, it just stops. So it's very, very short range. What's the consequence of that? The consequence is that we can combine two nuclei to make bigger nuclei. But to do that, you will have to bring them very, very close to each other. Yeah. मैं आपको दे दूंगा. So when you combine them, you can combine them. To combine them, what you would need to do, you would need to just bring them very close to each other to a distance of 10 to the minus 14 meters. If you are able to do that, this nuclear force is so strong, it will just take into effect and something will happen. Some chemical reaction will happen, nuclear chemical reaction. But first you need to bring them very close. And bringing them close is a problem because they are all positively charged. So when you're bringing them close, they're repelling each other. So if two things repel each other, how can you bring them together? Well, you smash them very, very hard so that the repulsion can be overcome. That's one method.
Sir, you said कि जो nucleons है, वो they are neutral charge.
No, nucleons, when I say nucleon, I mean two particles, protons and neutrons. Neutrons are neutral, but protons have positive charge.
But this force,
It acts between all nucleons, between protons, and neutrons. It doesn't care if you're a proton or you're a neutron. So you can say that there's strong nuclear charge on both protons and neutrons, but there's electric charge on proton, but not on neutron. Well, no, I'm not saying that if you bring a proton and neutron, they don't repel. But if you take one nucleus, let's say carbon and another carbon, carbon has 6 protons and 6 neutrons. So it at least has 6 charges, right? So if you bring 2 carbon nuclei together, they are repelling. And the simplest fusion, so what do I mean by fusion? I want to combine nuclei to make bigger nuclei. The simplest nucleus is just a proton, which is hydrogen. So if I want to bring 2 protons together and make a bigger one, make the next one helium, then they will repel. I'll have to do something to bring them together. So one thing you can do is smash them very, very hard at each other. And how do you smash them very, very hard at each other? Well, one way is that you just take your material and heat it to very, very high energies, very, very high temperatures. What's a high temperature? That means average kinetic energy or average speed of the constituents in your material is very, very high. So the atoms or the nuclei, well, actually, once you cross 2000 Kelvin, the atoms are all stripped out, the electrons are stripped out, and you basically have a soup of nuclei and the electrons separately. It's called plasma. So you have nuclei moving freely. So you heat them further, they are moving even faster. A stage will reach when you heat them to very high temperatures, when their speeds will be high enough so that they can overcome this repulsion, electrostatic repulsion, and come very close to each other. So it turns out that about 10 million Kelvin, Kelvin is same as centigrade, at about 10 million centigrade, this thing happens. Like if you have any kind of nucleus, let's say hydrogen, you heat it to 10 million Kelvin, they will start coming together to such a small distance that the nuclear reactions will start happening. And that's what they do in what they call tokamaks. You don't need to know this, but you may know that there are these machines on Earth where people can heat things to this much high temperature. You may have heard this news that China created an artificial sun. They didn't create an artificial sun. All it was, and they didn't create it now, they've been doing it for a long time. And not only China, the whole world has been doing it. So what they do is heat things to very, very high temperature, 10 million Kelvin, and then these fusions start happening. You can ask, it's just I'm now just throwing away some trivia, that how do they heat it up to 10 million Kelvin and where do they contain it? Why doesn't it like melt the things where it is? Essentially, you are hoovering it in vacuum. It's not touching anything. It's magnetic confinement, just like you may have seen those magnetic trains which just hoover. So you have put it in a kind of a magnetic kettle. So the material is just suspended. It's not touching anything. And then you heat it up by further magnetic heating. essentially throwing in currents inside, which heats it up. And there's kind of no limit, well, some limit, but people can heat it up to 10 million Kelvin. And why they're doing it? Because the idea is that we're going to get energy out of it one day. We can get energy, as I said last time, but it's not commercially feasible right now. And hopefully in the next 30, 50 years, when it becomes commercially available, then all this talk of green energy and what they call renewables and whatnot, it becomes completely irrelevant, because this thing has absolutely no greenhouse gases coming out, absolutely no waste products, nothing. It's just free energy forever. Just like we get from sun, that's free energy, and it's coming in the same way. So sometimes people explain it using E is equal to mc square. Although, and they present it as if this is special to nuclear reactions. There's not anything to do, it has nothing to do with nuclear reactions. It's true for any reaction. This equation just says that energy this, I think I should use some other program. This is very laggy. This says that it's not. What? हाँ मैं उसने अपने उस पर नहीं ना कर रहा किसी राइटिंग प्रोग्राम पे, that's why I'm doing it. और ये है अभी क्या नाम है माइक्रोसॉफ्ट का जो है, energy is same as mass. So what this equation says, this is a famous Einstein's equation. It says that if some energy comes out of a system, its mass must go down, because energy is equal to mass. So if you lost some energy, you must have lost some mass. And how do you calculate? Using this equation, with c square, you know, is a very, very big number. C is 3 into 10 to the 8, and c square is the square of that. So if I work in joules and kilograms and meters per second, it says that if I lose 1 gram, that will, to lose 1 gram of mass would mean that I have given out a huge amount of energy. Or if I lose 10 joules, then my mass will go down, but it will be so small, that it will be unperceptible as a percentage of the starting thing. But in nuclear reactions, the total energy which is going out is so big compared to the masses involved, is that it's not imperceptible, it is perceptible, and you can measure it. So for example, what I can do, I can combine 4 hydrogen to make 1 helium. And the mass of the helium nucleus is 0.7% less than the mass of 4 protons. So just a way to calculate how much energy is going out. So Einstein tells you that if you lose a lot of energy and you measure the masses will not match. Mass has decreased. So that's why if you combine 4 hydrogen, mass of helium nuclei is 0.7% less. So this is what happens. You combine 2 hydrogen, 4 hydrogen. So typically the reaction which is most relevant for what is happening in the sun and for what is also important in using this process to produce energy on Earth for commercial use, is this: combine 4 protons to make 1 helium. And as a result, some energy is released. Actually, a huge amount is released. Now, this graph is very important. There is something about this picture which you should object about, which I haven't, or at least point out. I haven't said it. Anyone wants to say it?
Velocity.
Not velocity. What about velocity? Yeah. So I started with 4 protons, and in the final thing, I have 2 protons and 2 neutrons. So something strange happened. So what happened was 2 protons turned into 2 neutrons. So that's part of the process, and we will see that it's going to be very important for us in how do we know, in knowing that is this really what's happening at the center of the sun. We haven't gone to the center of the sun, but this fact is gonna tell us what's happening at the center of the sun. But you should note that 2 protons have converted into 2 neutrons. So this typically happens in nuclear reactions. You do not change the number of total nucleons, but some protons change into neutrons and some neutrons change into protons. That can happen. Total number of neutrons and protons, they are not changed. But protons can convert into neutrons and neutrons can convert into protons. So this graph tells you that when you combine certain nuclei, what happens? So over here on the y-axis, you have mass per nuclear particle. For hydrogen, you have more mass per nuclear particle. If I combine 4 hydrogen to make 1 helium, my total mass per nuclear particle has gone down. That means in combining hydrogen to make helium, I have lost some mass. So that's an indication that some energy will go out in this reaction. Then if I combine helium to make carbon or oxygen, let's say I combine helium with some hydrogen to make carbon, then what's going to happen? My mass per nucleon has again gone down. So I've lost some mass. So where does it appear? It appears as the energy which is going out. You can think of it as binding energy instead of mass per nuclear particle, but this is the easiest way to think about it. And similarly, I can combine carbon to make oxygen and I'll again release energy. I can keep doing it, like I can combine some oxygen and other atoms to make iron. Again, I have lost some mass and that goes out as energy. On the other hand, after I cross iron, I go to, so on the x-axis, we have atomic mass. So each of this point over here is a different kind of nucleus. So you see that after crossing iron, when I go to the right, mass per unit, mass per nuclear particle is again increasing. That means if I break uranium and break it into lead and something, then the mass per nuclear particle has gone down. So mass has gone down. So again, some energy has to come out. That lost mass appears as energy, which goes out. So it tells you that using the nuclear chemistry, you have 2 methods of getting energy out. either take a small nucleus like hydrogen and helium and combine them to make a bigger nucleus. Some energy will come out. Or take a very heavy nucleus like uranium and bake it. Again, energy will come out. So this is what happens in conventional nuclear reactors. The nuclear reactors which we have already using commercially. You take uranium or plutonium, some very heavy nucleus, and bake it. Since you bake it, it's not called nuclear fusion, it's called nuclear fission. And energy comes out. You can see that in the fusion, the energy differences like this are much bigger than the energy differences are over here. So in the fusion reactors, not only you will create more energy, but there's a problem with these reactors. When you break apart the nuclei, you create the resultant products. They are radioactive. They give radiation. So you have to bury them somewhere. Otherwise, they're dangerous for all life. So that's the only issue with nuclear fission. Again, it doesn't produce any carbon, it doesn't produce any greenhouse gases. The only problem is that the nuclei it bakes into are not the isotopes which are very stable, are those things which give radioactivity. So you have to hide them somewhere. In any case, that's not our concern. But what you should note there are two methods. Yeah.
Can you just repeat the two methods? So one is when you break a heavy
Yeah.
like uranium, and what was the other one?
The other one is you take a light nucleus like over here and combine it. Because you see, like, think of it as an energy graph. You go down, it's like potential energy. So you're releasing something out. You go down, you're releasing something out. So either you can slide down from this side or you can slide down from this side.
When you combine them, that's fusion.
Yeah.
And then you break it, it's fission.
Yeah. So when you slide down on this side, you're taking some light nuclei and combining them together to get a bigger one. While over here, you are breaking apart a big nucleus. However, if you are right over here, like iron is right in the valley, you can't do anything with to iron to get any energy out. Because if you bake the iron, you are climbing the hill up here. That means you will not be releasing energy, you will have to provide energy to bake the iron. Or if you combine the iron to get a bigger nucleus, again, you will have to provide energy. You are climbing up a hill. You won't get any energy out, you will have to provide. So iron, in a sense, is the most stable nucleus because it doesn't give off energy if you bake it or if you combine it. You can't get energy out of iron. That's something special about iron. And this will again become kind of important for us. So in any case, so this in case of stars, what happens? They start with, as I said, with gases which are hydrogen. 70% hydrogen and about the rest is helium.
Sir?
Yeah.
Sir, if we provide energy to the iron, how would we know that we are moving for oxygen or we're going to get lead or uranium?
Well, it depends what you do. I'm not discussing what exactly will happen. You can probably make it move in either direction, depending on how you treat it. But the point is that whichever direction you move, whatever reaction you try to produce, you will have to give energy. It won't happen on itself, and it will not give you energy. Energy will not come out, energy will be absorbed. Now, what happens in case of these clouds of gases in the outer space, which we are now calling protostars when they are very, very heated up, since they have a big reservoir of hydrogen. So when the center is heated to 10 million Kelvin, this hydrogen starts going to nuclear fusion. It starts combining to make helium. And when that happens, energy is released. So it becomes a fuel, it becomes a source of energy. And it's only hydrogen which starts doing it first, not the helium, because helium requires even higher temperature. So hydrogen ignites first. And it makes sense because hydrogen has only one charge, which you have to combine, which you have to strike against each other. Helium has 4 times the charge. So it takes more higher temperature for it to combine. You go down here, bigger the nucleus, higher the charge. For them to combine, you will have to strike against each other at higher energies. That means higher temperatures. So to ignite any of these nuclei, to cause fusion, you need higher temperatures, and higher the nucleus size, higher temperature you need. So first, the hydrogen starts burning, and there's a huge amount of supply of hydrogen in these clouds. So the core starts burning. And when that happens, then we say that a star is properly born. So the previous thing was, it was just gestating, and now it's born. So it has its source of energy, which is not gravitational. So it stops contracting. It stops contracting. And when this happens, then we say that it has now entered its usual life cycle, its regular life cycle, which is, we call, it has entered the main sequence. And hydrostatic equilibrium implies that pressure at each point is equal to the weight of gravity. So it is only the inner core which is hot enough and at high temperature, high enough pressure where this happens. And star size becomes stable. That means it fuses hydrogen at exactly the same rate to balance out the gravity. How does that happen? Before we go there, so these are some examples. These are huge, big clouds of gases and dust in the universe where the star formation occurs. This is one of those. It's a very active area of star formation. So these are all like new stars. They are hazy because they're surrounded by, still they're new stars, so they're still surrounded by the gases, leftover gases from the clouds, from the gaseous clouds from which they were formed. So it's only the inner center which becomes a star, and even the inner center of the inner center, which is actually going through a nuclear fusion. So the outside gases, they're glowing, and that's how we see them over here. Lots of new stars are happening, and because of this new glow, the surrounding dust is also glowing. This, by the way, the Horsehead, famous Horsehead Nebula. So this is another example. You can see this is literally a cloud of gas and dust, and something in the center is ferociously glowing because a new star has born there. You can, definitely. You go there, touch it. What do you mean? They're just gases. They're like the way to think about it, we will look at the structure. The correct way to think about them is like the hot air balloons. That the center is the source of heat, and the outside is like a balloon. It's just expanded gases.
But you can't physically touch the source of heat.
Well, you go inside, you can. Well, no, it is kind of solid because the more you move in, it depends how you call solid. At such high temperatures, that's what I'm saying. At such high temperature, the states of matter it's probably not proper to compare them with what we see regularly. But what you can talk about is that they are at very, very high pressure when you go inside. So much higher pressure than this table. So they're very, very solid, but at the same time, they are malleable in some sense. This is in the infrared. It's an infrared picture. In infrared, you can see the clouds more clearly because they are not much heated. This is again a star formation area. So stars have this inbuilt temperature pressure thermostat. So they know at what energy level, at what power they should be burning their nuclear furnace. So they have a nuclear furnace inside. They know at what power the nuclear furnace should be burning so that they are stable in size. Like sun, what it doesn't do is give one energy one day and then a huge amount of energy the other day. It's very stable. Why is that happening and why is size is stable? So it's because of this temperature pressure thermostat. So what's happening is that you have this inner core and there's nuclear reactions happening here. And one should think that there's this rest of the star, most of the star. It's all crushing onto this nuclear core. It's a very bad program. So this whole star is crushing onto the nuclear core. So all that weight, the inner core has to sustain. Why should it sustain it? It won't. It will crush down and start contracting. And we know when it starts contracting, what happens is when anything starts contracting, it heats up. That's what we decided. But that's the thing we want to stop. And it is naturally stopped because what happens is that you have this hydrostatic equilibrium and there's a natural temperature pressure thermostat. Because what happens is, so suppose if the nuclear reactions are not set up at high enough rate to fight the gravity, what's happening is that the gravity is pushing down and this pressure it's not writing. This pressure, because of the reactions created by which are happening inside, is balancing it. If this pressure is a bit less, if the nuclear reactions go down, they are not set up at a high enough temperature, what's going to happen is that the gravity is going to crush it. When gravity crushes it, it heats it up further. So temperature goes up. And these nuclear reactions, the rate depends on the temperature. So when the temperature goes up, the nuclear furnace, it starts igniting at a higher rate. So it pushes back against the gravity. On the other hand, if in the beginning, the nuclear furnace is set up at a higher rate than required to exactly balance the gravity, what's going to happen? It's going to expand. The core is going to expand because it has more pressure than required to balance the gravity. So when it expands, it cools down. So remember, with these gases, whenever they contract, they heat up. Whenever they expand, they cool down. So as it expands, it cools down. And when it cools down, the rate of reaction goes down because nuclear reaction rate is directly proportional to the temperature. So it expands, cools down, and the rate goes down. So the gravity again wins. Gravity crushes it back. So
What did you say was that conclusion?
the reaction rate is proportional to the temperature. Higher the temperature, higher the reaction rate. So you can see there's an equilibrium which is naturally achieved. Before, it was just crushing when there was no nuclear reactions. It was just contracting, contracting, and heating up. Now there's a nuclear source which has stopped it. And the nuclear source knows that it has to burn at a particular temperature to exactly balance the gravity. Because if it doesn't balance, it's going to contract and heat up to increase up the rate. So naturally, the rate is increased. And if the rate is increased much more than required, it will expand, and naturally the rate will be decreased. So an equilibrium is achieved. And what does it depend? It depends only on the gravity. How much is the crushing happening? So it will depend on how big, how massive is the star, how much weight it has to sustain. Is this process clear? That you have a lot of weight crushing in, and the thermostat is such that it has to sustain this weight in an equilibrium. And it can do it because when it crushes, the weight goes up, and when it expands, the weight goes down. So you achieve a kind of an equilibrium, which is when the star becomes stable and when we say that it enters the main sequence. So actually on this diagram, there are some stars here. They're dim and not very hot, but very near the main sequence. Those are the protostars. So when the nuclear furnace ignites, they enter the main sequence. And in the main sequence, before they enter the main sequence, their size is constantly decreasing. Once they enter the main sequence, the size is stabilized. Size is stabilized, and also the nuclear furnace is now burning at one particular rate. The rate is not changing because the rate is there to exactly cancel the gravity. So for years and years and years, until they run out of the fuel, they're going to be very stable in terms of their size and in terms of the rate at which the nuclear furnace is burning, because they are both, those two are related. So this explains this pattern, one of the patterns which we saw in the HR diagram, that more massive a star is, higher the weight. Remember, we drew those lines over here. Like over here, we know that these stars up on the main sequence, they are more massive compared to this one, our sun. As you go up on the main sequence, the stars are heavier. Wait. Why they are heavier? Because heavier stars have to hold up more of the weight. And to hold up more of the weight, they have to burn their nuclear furnaces at higher rate. So when they burn the nuclear furnaces at higher rate, they're giving out more energy. Whatever energy is produced in the nuclear furnace finally comes out, because nothing can remain inside, right? If it remains inside, it's going to heat it up. It's in equilibrium, nothing is being heated up. So everything, every nuclear reaction, every energy which is produced finally comes out. So for massive stars, you have the nuclear furnace is tuned up to higher reaction rate. That means they give off more total energy. That's why they are more luminous. And that's what you see over here. As you go up on the main sequence, you have more luminous stars. And these more luminous stars have higher mass. And it's not just the words, the way I'm explaining. People do actual calculations, they do simulations, and then they try to match that how big of a mass should be giving off its temperature. These are called stellar models. That if you have a bigger mass, at what mass, what should be the weight of your nuclear furnace to sustain it? And as a result, what should be the luminosity of such a star? And then you match with what you see on your main sequence. And our matches are very, very good. So our stellar models do a very good job to explain where these stars should be and what their masses should be. This is just one of the things which can be explained about this HR diagram from what I have said so far. It also explains why main sequence goes diagonally on the HR diagram, because a higher pressure requires higher temperature of the core, which result in higher temperatures of the outer surface. But this connection is not always true. We will see that it breaks as well. This connection is true in main sequence, but not always true. So the core and the outer surface, sometimes they act very differently. But this part has to be true. Massive stars have to sustain higher weight, so they burn at higher temperature. So higher luminosity. The core is at higher temperature. That doesn't mean that the outer surface have to be at higher temperature. It may logically make sense. Maybe the outer surface is also at higher temperature, but not always. As I said, we will see that one should think of stars as these hot air balloons. So if the balloon is very, very big, the inside furnace may be at a very high temperature, but the balloon can expand and cool down. So that kind of a thing can happen. This also explains, as I said, that heavy stars, they live for a very short amount of time. How do we know? We don't know that. That's only what our models tell us. We haven't, no human has lived, or the science hasn't been old enough to keep observing some stars and measure their ages. It's just our models which tell us, and we have a lot of data to confirm it, indirect data, indirect knowledge. But it's our model which tell us that to sustain a heavy star, you have to turn up your nuclear furnace at a very, very high rate. That means you consume your fuel, you're just burning out your fuel. It's like driving a gas guzzler and you just burn off your fuel very, very quickly. So you can't be shining for a long time. So that's the reason that the lighter stars, they live for longer time compared to heavier stars. Our sun is expected to live 10 billion years in total, out of which 5 billion it has already passed. But very heavy stars, they may even live for only for 1 million years. And much bigger stars can live up to 100 billion years. Much smaller stars. This is not that important, except for, well, this is important in a sense. Yeah. So this is what happens in sun and in all stars. Well, at least in the what you call low mass stars, is that you combine 4 hydrogen. So P stands for proton. There's even a key over here. And then you combine them finally to make 2 protons and 2 neutrons. It happens to various steps that shouldn't concern us much. But what one should note is the thing which I told you before, that 2 protons are changing into 2 neutrons. So how does that happen? Well, the way it happens is a proton is converted into a neutron. But a proton has a charge and neutron doesn't have a charge. And you may have read somewhere that the charge cannot be created or destroyed. So what happened to the charge of proton? Well, what happens is a positron goes out. Positron is just like an electron. It's just the antiparticle of electron. Antiparticles are particles which are just like the particles, except that their charges are reversed. So it's like an electron, but with a positive charge. It's electrons, not even cousin, twin, with a positive charge. And also there's another particle called neutrino, which goes out. It just so happens that this happens in this reaction. And finally, you end up with 2 neutrons and 2 protons. We have to, this class goes up to 110, right?
Yes, sir.
So this reaction, we need to study it in a bit more detail. But this is the summary of what I did in the last lecture, and actually I finished it only in this lecture. So clouds of gas contract under their own gravity. The process produces heat and the temperature and pressure inside the cloud rises. It's just like a gas, nothing fancy. As the cloud heats up, it radiates more and more, but still keeps heating up. That was the strange thing about these gravitational objects. That as they contract, they give off energy, as they give off radiation, but as a result, they don't cool down. They actually heat up. This is a runaway process and cannot stop without an extra source of heat inside the cloud. Because when they heat up, they give off more radiation. And the more radiation they give off, the more they have to contract and the more they have to heat up. So it's a completely runaway process unless there's a new source of energy to produce extra pressure to stop the crushing of gravity. So that source of energy is provided when the core heats up to 10 million Kelvin and hydrogen starts fusing to form helium. And you get energy. That energy finally trickles out of the gas and gives us the power of a star. So whatever energy is produced in this nuclear furnace has to come out. It trickles out, and when it trickles out, it forms the light of the star. There should be a couple of questions you may be asking. So like everything started from gas. And I say that if there's no source of, if there's no extra source, the gas cloud keeps contracting and heating up. So why is Jupiter not a star? Why is Earth not a star? Why is this table not a star? Why is this table not crushing under its own gravity? So these are important questions. And table may be taking it a bit too far, although the principles are exactly same. But a very pertinent question is about Jupiter. Why is Jupiter not a star? Why is Jupiter contracting? Is it heating up? Will it become star one day? Or will it not? And why it hasn't in 5 billion years? So these are just questions for future, which we will discuss. So all of this, one can ask that what is the evidence? So we are saying that all of this is happening inside the core. As you said that no one has touched a star, let alone its core. So how do we know this is happening? Like the other things, like those measurements, that what is the temperature of the surface, those things were very easy because it's just the light and its spectral analysis. What happens inside is not directly observable because what happens is this core This core produces some energy. I don't know why it's doing today. Maybe it's the internet. This core produces energy. It heats up the outer layers. And the outer layers, they just then give off the thermal radiation. So everything which happens inside is lost. All that information is lost. The only information we get is what is the temperature at which the outer layers are heated. So that temperature is not very high, about 6,000 Kelvin. But in any case, we don't know what happened inside. Whatever happens inside, its only job is to, from our observation point of view, to keep the outer layers warm. So how do we know what happened inside? Well, the clue is these particles, neutrinos, which I told you, they are produced in this reaction. When two protons are converted into neutrinos, some particles are produced, some ghostly particles, which are called neutrinos. These guys. So this process, which converts protons into neutrons, well, I should have put in and a neutron. This is the fourth force which I was talking about. This is responsible for radioactivity and actually for the burning of the sun. This is called the weak nuclear force. If this force were not there, there would be no sun, no star at all. So what does it do? It can convert a proton, because for the fusion to happen, what you could do, you could take two protons and combine it into a nucleus consisting of two protons, but there's no nucleus of two protons. There's deuterium, which has one proton and one neutron. Or you can take four hydrogens and combine them to make a nucleus of four protons. It so happens that nuclei, they need both protons and neutrons. I'm not obviously going to go into detail why is that so, but it's just a fact. It's a fact about nuclear forces. They need neutrons. There are no nuclei which are just consisting of protons. You need neutron. Neutron is like a glue for the nuclei. You need neutrons in there. Usually as much neutron as protons. And for heavy nuclei, even more. So like if you look at the table of the nuclei, the heavier the nucleus is, it has even more neutrons than protons. So to get this fusion reaction going, you have to convert a proton into neutron. And that happens in these reactions, which are called weak nuclear reactions. So what it does, for example, it takes a proton, converts it into a neutron, and a twin of the electron. It's just like electron, but with the other charge. And some energy which is just light. And another particle, which you may not have heard of, or you may have, it's called neutrino. It's a very ghostly kind of particle. Have you heard of it? Big Bang theory. So they're just a fundamental particle. What's so funny about neutrinos? Huh? क्यों? I know it's funny, but it's completely misrepresenting the physicists. You don't agree? Okay. So neutrinos are a kind of a fundamental particle. As I told you the other day, that there's a new periodic table in town. Previously, people thought a century ago or a century and a half ago that they are, well, you know, the idea came from Democritus that everything is made up of some fundamental entities. And then they said, well, maybe these entities have certain forms. There are certain kinds of entities. Like, for example, Aristotle thought that there are 4 fundamental forms: earth, fire, air, and water. So this idea was there. And at the end of the 19th century, or in the middle of the 19th century, people thought, because they were doing lots of chemistry, they thought there are fundamental particles, they're fundamental elements. Everything is composed of those elements. Because they knew that when you make new chemicals, there are certain essential chemicals, elements, which are basically getting exchanged. So they thought these are the fundamental objects, which were called the atoms or elements. But very soon, people realized that the atoms are not fundamental. They are composed of other things, which are called electrons and nuclei. And then people realized that the nucleus is proton and neutron. This is the latest picture we have. And you can essentially, this is now telling us that these are the fundamental particles. We haven't been able to break them. We don't know if they are composed of anything else. These are the fundamental things of which everything in the universe is made of. And you can essentially forget about the second and third column and just concentrate on the first column. Everything you have seen in your life is composed of the first column and the last. Well, this is the light. And these things are there to bind the nucleus together, these gluons. And these 2 particles are there to cause the change of proton into neutron. Forget about these guys. These are just the cousins of these, and no one knows why do they exist. They're just the copies of the first column, but a bit heavier. And there's a very important question in the fundamental theory of physics, is that who ordered these? Who ordered these 2? These are called the second and third generation. They are copies, heavier copies, but why do they exist? No one knows. But let's forget about that. Let's concentrate on the first column. It says that there are only 4 fundamental particles. One is electron, everyone knows about them. And the proton and neutron, they are composed of up and down. You don't have to know the detail, but it's nice to know. They are composed of further particles called quarks. So each proton is 3 quarks, each neutron is 3 quarks. A proton has 2 up and 1 down, and a neutron has 2 down and 1 up. But there's this extra guy, neutrino, which is not part of the matter. It just flows freely. It's not like up and down, they combine to give us various nuclei. An electron is obviously there to complete the atom. What neutrino does, it doesn't stay inside any of the material. It's like light in some sense. So the neutrinos, they don't have mass. Well, now I'm going to tell you at some point that they do have mass, but for a long time, people thought that they don't have mass. These guys have tiny masses, because you know the proton has mass. You memorized it in your 10th grade chemistry. Electron has a mass 9 into 10 to the minus 31 kilograms. This guy doesn't seem to have a mass. At least people thought that it doesn't have a mass for a long time. So in this sense, this is just like the photon. Photon doesn't have a mass. And anything, Einstein's theory says that anything which doesn't have a mass must move at the speed of light. It cannot stay still. So light always moves at the speed of light. We studied this, we learned this at the very start of the course. So same is true for neutrinos, because they don't have a mass. So they can't stay inside matter. They have to keep moving at the speed of light. But they do interact. That's how they are produced. And these equations are just like your 10th grade chemistry equations. Remember what you used to do with them. What you used to do with them is you used to say, I can bring these things to the other side, and that's also a possible reaction. Right? You used to have these like carbon combining with something, and you can move these things to the other side, and that's also a possible reaction. So you can bring the neutrino over here, and then one possible reaction is you hit a proton with a neutrino, and it will convert it into a neutron and a positron. So they do interact with the matter. One way of interacting is that they can hit a proton and convert it into a neutron. And since they can do that, just like chemical equations, you can bring it to the other side, and one possibility is that the proton just breaks into a neutron and a neutrino. So that's how they're produced, and this is how they can be detected. If you put certain material in front of it, it's going to hit it, and oh, I think I'm running out of time. Is it?
Ran out of time.
Okay. So we will complete this story. This is going to be quite fun, and it turns out that we have huge evidence in favor of this cool story which I told you, and it's based on neutrinos, but we will do it next time. Maybe we should have a class. Oh, we have Thursday, so we will have a class after Thursday because we have to make up a bit. It's up to people. Do you guys want to come? Okay, then we'll do hybrid. But then we will have an online class on Friday or something.
Yeah, so Friday will be good.
Okay.
I don't think Friday will work because some of us have classes on Friday. Like,
Till when?
Like from 10 to 5:30. No, 4.
How about at 8 or 9?